Hi, my name is Emily Torres, and I'm a sophomore at the University of Tennessee in Knoxville. My major is mechanical engineering, but the research I'm presenting is aerospace-based. What I'm presenting today is using the class-shape transformation method with the double cosine distribution. Now, before I explain what these two concepts are, I'd like to give a brief overview of what area of aerospace engineering these topics are in. What I focused on over last summer was an optimization of airfoils. This is an important aspect of aerodynamic research because with maximum or minimum constraints added, we can get more efficient flight variables like more lift, less drag, better pressure distributions, and smoother gradual compressions. So I mentioned optimization of airfoils. What are airfoils? An airfoil is the cross-sectional area of the wing of a plane. As you can see on the right image, this is typically what they look like. When getting into optimization, we work with airfoils and we alter their geometry. The first thing I did in this research was apply the class-shape transformation method to the airfoil RAE 2822. RAE 2822 is a specific airfoil and it consists of a list of coordinates that define the shape. That's the graph on the left. On the right, the class-shape transformation method was added. What is this? Well, the class-shape transformation method consists of two equations, the class function and the shape function. The class function is applied first, and it defines the general geometry of the airfoil. The shape function comes next, and we get the graph on the right. This method is important because it basically decomposes the airfoil into something we can work with and manipulate for optimization. Next, I added the correction to the shape graph. As you can see on the left, it isn't continuous, so it's harder to alter the geometry. On the right graph, I multiplied the lower surface by -1 to get a continuous function. This makes it easier to make changes to it. Now we apply the double cosine distribution to the class-shape function of the airfoil. What is the cosine distribution? Well, this image really helped me understand it. Basically, what we're trying to get from this method is more clumped points on the trailing edge and the leading edge. Alongside doing this, we get more spaced out points in the center as well. This is helpful because it gets us more control over the more critical regions of the airfoil. It can help in getting more accurate results when optimizing. With the double cosine distribution added, we can generate a complete new set of points with more clumped points towards the end and slightly more spaced out points in the center. Well, why do we care about this? Why does this matter? Well, because many issues with optimizing airfoils are that there are too many points for the optimizers to handle, and therefore we get inaccurate results. But with more points of the airfoil in general, the more control we get. So there's a problem, and that's why more research is still being conducted. With the double cosine distribution, we get a new set that can be the same amount or more as the original set, but the points are more clumped at the ends and thin in the center. This is where I applied the double cosine distribution to the class-shape function of the airfoil. Notice it looks exactly the same as the original graph, and you can tell almost no difference. You see the differences on the next few slides when looking more closely at the old and new coordinates. So here is a short comparison of the points leading to 1 for the x values. As you can see, with the new x's, it's closer to 1 than the original x's. The same is with the s values, except they're closer to 0.2127. These coordinates are of the other side of the trailing edge, and again, the new x's are closer to -1 than the old x's. This is the last comparison, and it's the coordinates at the center where the leading edge is. Unfortunately, we get slightly more spaced out points here for x and s in this new set. It would be more desirable to get it more clumped together. In conclusion, the double cosine distribution, also known as cosine spacing, clumps the x and s values more on the trailing edge, but it spaces them out on the leading edge. An alternative approach could be to use the cosine distribution on the airfoil first, so we can get clumped points on the trailing edge and on the leading edge, and then applying the class-shape transformation method next. More research is still being conducted, but I'm very, very excited to see newer ideas advance aerodynamic optimization. Thank you for watching and thank you for your time.